For 25 years, scientists believed they had solved the universe. One elegant model explained nearly everything: the age of the cosmos, the arrangement of galaxies, the afterglow of creation itself. It predicted observations with breathtaking accuracy. Textbooks were written around it. Nobel Prizes were awarded because of it. It was, by almost every measure, the most successful framework in the history of cosmology. Then, the James Webb Space Telescope opened its golden eye and looked deeper than any instrument before it. What it found does not destroy the model. It does something more unsettling. It reveals a place where the model quietly stops working. A crack, thin, precise, and running through the foundation of everything we thought we understood about the cosmos. If this kind of deep science matters to you, a like and subscribe genuinely helps us keep going. We put serious research into every single one of these, and your support makes the next one possible. Are you comfortable? Now, let's begin. There is a moment in the history of any science where the puzzle seems finished. The pieces fit, the predictions land, the experiments confirm what the equations said they would. And for a brief window, the people doing the work allow themselves to believe they might actually understand the thing they have been studying. Cosmology reached that moment near the turn of the 21st century. And what scientists believed they understood was nothing less than the entire universe. The story of how they got there begins almost 100 years earlier, in a small office at the Mount Wilson Observatory, overlooking the city of Los Angeles. The year was 1929. The man sitting at the desk was Edwin Hubble, and what he had just discovered would eventually dismantle every assumption humanity had held about the cosmos for thousands of years. Hubble had been studying galaxies. At the time, most astronomers were not even sure galaxies existed as separate objects. The prevailing view was that the Milky Way was the universe. Everything visible in the night sky was thought to be contained within a single enormous island of stars. Hubble proved that wrong. Using the 100-inch Hooker telescope, then the most powerful instrument on Earth, he measured the distances to faint spiral nebulae and showed that they were far too distant to be part of our galaxy. They were galaxies of their own, millions of light years away, separated from us by voids so vast that light itself needed eons to cross them. But Hubble did not stop at distances. He also measured velocities. And what he found was something nobody expected. Nearly every galaxy he observed was moving away from us. The further a galaxy was, the faster it receded. This was not random motion, it was a pattern. A relationship so clean and so consistent that it could be written as a simple equation. Velocity equals distance multiplied by a constant. That constant would eventually carry his name. The Hubble constant. The implication was staggering. If every galaxy is moving away from every other galaxy, and the further apart they are, the faster they separate, then the universe is not static. It is expanding. Space itself is stretching, carrying galaxies with it the way dots on the surface of an inflating balloon move apart even though nothing is pushing them. They are not flying through space. Space is growing between them. That single realization changed everything, because if the universe is getting larger now, then it was smaller in the past. Run the clock backward far enough and every galaxy, every particle, every scrap of energy that exists today was once compressed into a state of unimaginable density and heat, a beginning. Not a beginning in the way a story begins, with a first sentence on a blank page. A beginning in the way reality begins. A moment before which there was no space, no time, no physics, as we understand it. Scientists would eventually give that moment a name, the Big Bang. The name is slightly misleading. It was not an explosion in space. It was the rapid expansion of space itself, from an initial state so hot and dense that the laws of physics as we currently understand them did not yet apply. Everything that exists, every star, every planet, every atom in your body, emerged from that expansion. The elements in your bones were forged in the nuclear furnaces of stars that formed from gas that cooled out of the aftermath of that primordial event. You are, in a very literal and physical sense, a consequence of the Big Bang. But for decades after Hubble's discovery, the Big Bang model was just one of several competing ideas. Some scientists preferred a steady-state universe, one that had always existed and always would, with new matter constantly appearing to fill the gaps created by expansion. The debate was real, the arguments were fierce, and neither side had a decisive piece of evidence. Light released roughly 380,000 years after the Big Bang, when the universe had cooled just enough for atoms to form and photons to travel freely for the first time. That ancient light had been traveling through the expanding universe ever since, stretched by the expansion of space from its original searing intensity into the faint microwave glow that Penzias and Wilson were detecting. The existence of this radiation had been predicted 17 years earlier by physicist George Gamow and his colleagues Ralph Alpher and Robert Herman. If the Big Bang was real, they argued, its thermal afterglow should still be detectable as a faint background signal filling all of space. The temperature they predicted was remarkably close to what Penzias and Wilson measured, approximately 2.7 degrees above absolute zero. That detection transformed cosmology overnight. The steady-state model could not explain a uniform background glow left over from a hot, early state. The Big Bang could, and from that point forward, the expansion of the universe from a hot, dense beginning was no longer a hypothesis. It was the foundation on which everything else would be built, but the foundation was still incomplete. Scientists knew the universe was expanding. They knew it had begun in a hot, dense state. They had the afterglow to prove it. What they did not yet know was what the universe was actually made of, how fast it was truly expanding, or what its ultimate fate would be. Those questions would take another 3 decades to answer. And the answers, when they came, would be among the strangest discoveries in the history of science. The first great surprise was dark matter. By the 1970s, astronomers had noticed something profoundly wrong with how galaxies behave. Stars at the edges of spiral galaxies were orbiting far too quickly. According to the laws of gravity, stars that far from the galactic center should be moving slowly. The way the outer planets of our solar system orbit more sluggishly than the inner ones. Instead, the outermost stars were racing along at speeds that should have flung them out of the galaxy entirely. Something unseen was holding them in place, something massive, invisible, and distributed in an enormous halo around each galaxy. Astronomer Vera Rubin provided the most compelling evidence for this invisible substance through meticulous observations of galaxy rotation curves throughout the 1970s and 80s. Her data showed a consistent pattern across galaxy after galaxy. Visible matter alone could not account for the gravitational forces at work. The galaxies were behaving as though they were embedded in vast clouds of invisible mass, roughly 5 to 6 times more matter than the stars and gas and dust that telescopes could actually see. That invisible mass was named dark matter, not because it is literally dark, but because it does not interact with light. It does not emit photons. It does not absorb them. It does not reflect them. It interacts with the rest of the universe only through gravity. And despite decades of effort, no experiment has ever directly detected a dark matter particle. We know it exists because we can see what it does. We can watch its gravitational fingerprints on the motion of galaxies, on the bending of light around massive clusters, on the structure of the cosmic web that connects galaxies across hundreds of millions of light years. But we have never held it, never captured it, never identified what it actually is. The second great surprise came in 1998, and it was far stranger than dark matter. Two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, were using a specific type of exploding star to measure the expansion history of the universe. Type Ia supernovae are extraordinarily useful because they all explode with roughly the same intrinsic brightness. That makes them cosmic yardsticks. By comparing how bright a Type Ia supernova appears to how bright it should be, astronomers can calculate its distance. And by measuring the redshift of the light from the supernova's host galaxy, they can determine how fast that region of space is expanding. The teams expected to find that the expansion of the universe was slowing down. Gravity, after all, pulls matter together. 14 billion years of gravitational attraction between every particle in existence should be gradually decelerating the expansion, like a ball thrown upward that slows as it rises. Instead, the supernovae told the opposite story. The expansion of the universe is accelerating. Distant supernovae were dimmer than they should have been, meaning they were further away than expected, meaning space between us and them had expanded more than gravity alone should have allowed. Something was not just resisting gravity, something was overpowering it. Something was pushing the universe apart with increasing force. That something was named dark energy, and its discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. Dark energy is not a substance in the way dark matter is a substance. It does not clump into clouds or concentrate around galaxies. It is a property of space itself, a constant energy density woven into the vacuum of emptiness. Every cubic meter of the universe, no matter how empty it appears, no matter how far it is from the nearest star or atom, contains a tiny amount of energy. That energy does not dilute as space expands. That is the crucial difference between dark energy and everything else in the cosmos. Matter dilutes, radiation dilutes. As the universe grows larger, the density of matter and radiation drops because the same amount of stuff is spread across a greater volume. Dark energy does not follow that rule. New space comes into existence with its own dark energy already built in. The density stays the same, no matter how much the universe expands. Think of it this way. Imagine a vast ocean where every cubic meter of water contains a tiny amount of heat. Now imagine the ocean is expanding, growing larger every second. Normally, you would expect the temperature to drop as the same heat is spread thinner. But in this strange ocean, every new cubic meter that appears arrives already warm. The temperature never drops. The total amount of heat in the ocean keeps growing, not because anything is adding heat, but because there is more ocean. That is dark energy. And its gravitational effect is the opposite of everything else in the universe. While matter pulls inward, attracting other matter through gravity, dark energy pushes outward. It exerts a repulsive gravitational effect that accelerates the expansion of space. Individually, the energy in any single cubic meter is negligible, far too small to measure in any laboratory. But the universe contains an incomprehensible volume of space, and across that volume, the cumulative effect of dark energy dominates everything else. It is the single largest component of the cosmos, and it creates a feedback loop of extraordinary power. The more space expands, the more vacuum there is. The more dark energy accumulates, the faster the expansion becomes, which creates more space, which generates more dark energy, which accelerates the expansion further. The simplest mathematical description of this effect is the cosmological constant, a single number, usually represented by the Greek letter lambda, that assigns a fixed energy density to every point in empty space. Albert Einstein himself had introduced the cosmological constant in 1917, not to explain accelerating expansion, which had not yet been discovered, but to prevent his equations from predicting a universe that was either expanding or contracting. He wanted the cosmos to be static, eternal, unchanging. The cosmological constant was his mathematical patch. When Hubble later showed that the universe was indeed expanding, Einstein reportedly called the cosmological constant his greatest blunder and abandoned it. 80 years later, the supernova teams brought it back. The cosmological constant turned out to be exactly the term needed to describe dark energy, a fixed, repulsive energy embedded in the vacuum, constant across all of space and all of time, driving the acceleration that the supernovae had revealed. But there was a problem with the cosmological constant that predated the supernova discovery, and that remains unresolved to this day. Quantum field theory, the framework that describes the behavior of particles and forces at the subatomic level, predicts that the vacuum of empty space should be seething with energy. Virtual particles flicker in and out of existence constantly, and their cumulative contribution to the energy of the vacuum can be calculated. When physicists did that calculation, the answer they got was absurd. The predicted vacuum energy was roughly 120 orders of magnitude larger than the value the cosmological constant actually requires. That is not a factor of 10 or 100. It is 10, followed by 120 zeros, a number so grotesquely large that the disagreement between prediction and observation has been called the worst prediction in the history of physics. No one knows why. The cosmological constant is so small. No one knows why it is not zero, and no one knows why it takes the specific value it does. The standard model of cosmology treats it as a measured parameter, a number determined by observation and plugged into the equations, rather than a number derived from first principles. It works. It fits the data, but it carries a deep theoretical discomfort that cosmologists have lived with for more than 2 decades. This discomfort matters for our story. Because the lambda in Lambda-CDM, the cosmological constant, the fixed dark energy density that drives the accelerating expansion, was always the least understood part of the model. It was the component with no theoretical derivation, no microphysical explanation, and no answer to the question of why it takes the value it does. When the model was working perfectly, that discomfort could be set aside. When the model began showing cracks, the discomfort became harder to ignore. And when an independent experiment began suggesting that dark energy might not be constant at all, the discomfort moved from the background to the center of the conversation. But we are getting ahead of ourselves. By the late 1990s, cosmologists had assembled a picture of the universe that was bizarre, but mathematically coherent. Roughly 5% of the universe is ordinary matter, the atoms, the molecules, the stars, the planets, the people. Roughly 27% is dark matter, invisible, detectable only through gravity, essential for explaining the structure of galaxies and the cosmic web. And roughly 68% is dark energy, a mysterious, repulsive influence embedded in the vacuum of space, driving the accelerating expansion. This picture was given a name: Lambda-CDM. Lambda stands for the cosmological constant, the simplest mathematical description of dark energy. CDM stands for cold dark matter particles that move slowly compared to the speed of light. Together, Lambda-CDM became the standard model of cosmology, the framework that described the composition, history, structure, and fate of the observable universe. And then the Planck satellite confirmed it with a precision that stunned the scientific world. Planck was a European Space Agency mission launched in 2009. Its purpose was to measure the cosmic microwave background, that ancient afterglow from 380,000 years after the Big Bang, with greater accuracy than any instrument before it. What Planck delivered was a temperature map of the entire sky, showing the faint hot and cold spots in the microwave background with a resolution and sensitivity that bordered on the miraculous. Those tiny temperature variations, differences of roughly 1 part in 100,000, are not random noise. They are the frozen imprint of the density fluctuations in the early universe. Regions that were slightly denser than average in the first few 100,000 years would eventually collapse under their own gravity to form galaxies and galaxy clusters. Regions that were slightly less dense would become the vast empty voids between them. The pattern encoded in the cosmic microwave background is, in effect, the blueprint for every large-scale structure in the universe. Lambda-CDM predicts what that pattern should look like. It predicts the size of the hot and cold spots. It predicts their statistical distribution. It predicts how they should be correlated across different angular scales on the sky. And when the Planck team compared the model's predictions to their data, the match was extraordinary. 6 numbers. That is all Lambda-CDM needs to describe the observable universe as seen through the cosmic microwave background. 6 parameters: the density of ordinary matter, the density of dark matter, the age of the universe, the rate of expansion, the amplitude of initial fluctuations, and the way those fluctuations scale with size, and from those 6 numbers, the model reconstructs the full statistical pattern of the microwave sky with a fidelity that almost no one had dared to expect. The age of the universe came out to approximately 13.8 billion years. The geometry of space came out flat, consistent with the prediction that the total energy density of the universe is precisely balanced at the critical value. The expansion rate, the Hubble constant, came out to approximately 67.4 kilometers per second per megaparsec, and the composition matched the expected ratio of ordinary matter to dark energy within extraordinary margins. It is difficult to overstate how rare this kind of success is in science. Cosmology had gone from a field where the Hubble constant was uncertain by a factor of 2 to a field where 6 numbers described the observable universe to better than 1% accuracy. Lambda-CDM was not a rough sketch. It was a precision instrument, and for nearly every observation, scientists threw at it the distribution of galaxies across the sky, the way light bends around massive clusters, the relative abundances of hydrogen and helium and lithium forged in the first few minutes after the Big Bang. The model held. Conferences celebrated the era of precision cosmology. Papers used phrases like concordance model, meaning a framework where multiple independent lines of evidence all converge on the same answer. Graduate students were trained within Lambda-CDM the way engineering students are trained within Newtonian mechanics, as a framework so well tested that it functions as the default description of reality unless proven otherwise. And there were good reasons for that confidence. The model did not merely fit one observation. It fit thousands of observations, from the largest scales in the observable universe down to the statistical properties of galaxy distributions measured by surveys covering millions of square degrees of sky. It survived every challenge, explained every anomaly, absorbed every new data point. It was, by any reasonable standard, the most successful quantitative model of the physical universe ever constructed. But there is a quality that the most dangerous cracks share. They form in the strongest materials. A wall made of loose stones can shift and settle without breaking. A wall made of precisely engineered concrete can look flawless for decades, and then one thin fracture, almost invisible, propagates through the entire structure because the material is too rigid to bend. Lambda-CDM is that wall. Its strength is its precision. Its vulnerability is the same precision, because when a model predicts an observation to within 1%, A discrepancy of 5% is not noise, it is a signal. And when that signal persists after every possible source of error has been investigated and eliminated, it is no longer a discrepancy, it is a crack. The instrument that would expose that crack was not designed to be a revolutionary. It was designed to be a perfectionist. The James Webb Space Telescope was conceived in the 1990s when the standard model was still being assembled. Its scientific goals were straightforward by cosmological standards: observe the first galaxies, study the formation of stars and planetary systems, examine the atmospheres of exoplanets, and push infrared astronomy to depths that no prior telescope could reach. Webb was built to refine our picture of the universe, to add detail to the portrait that Hubble, Planck, and decades of ground-based observation had already sketched. Nobody expected it to find something that the portrait could not accommodate. Nobody expected the details to contradict the frame. The telescope launched on Christmas Day, 2021, aboard an Ariane 5 rocket from French Guiana. It traveled to a point in space called the second Lagrange point, roughly 1.5 million kilometers from Earth, where it unfolded the largest mirror ever sent into orbit 6.5 meters across, coated in a microscopically thin layer of gold to optimize infrared reflection. A sunshield the size of a tennis court deployed beneath it, dropping the operating temperature of the instruments to roughly -230 degrees Celsius. At those temperatures, the telescope's own thermal radiation would not contaminate the faint infrared signals arriving from the edge of the observable universe. The engineering was extraordinary. The mirror was composed of 18 hexagonal segments that had to align to within a fraction of the wavelength of infrared light. The deployment sequence involved over 300 single points of failure, any one of which could have ended the mission. Every one of them worked. When the first calibration images arrived, astronomers saw the universe at a depth and clarity that surpassed every expectation. Stars that Hubble had blurred together into indistinct smudges resolved into individual points of light. Galaxies that had been invisible at optical wavelengths appeared in the infrared, their ancient light captured after a journey of more than 13 billion years. The telescope was not just working. It was performing at the limit of what the laws of physics allow for an instrument of its size and location. The mood in the astronomical community during those early months was something close to elation. Webb was not just meeting its specifications, it was exceeding them. The instrument that had taken 2 decades and billions of dollars to build was delivering images and spectra with a quality that even its most optimistic designers had not quite dared to promise. For the scientists who had spent their careers building the concordance picture of the universe, Webb represented the final brushstroke, the instrument that would bring the portrait into its sharpest possible focus. The questions it was designed to answer were important, but they were expected to be refinements of an established picture, not challenges to it. How exactly did the first galaxies form? What were their chemical compositions? How quickly did star formation begin? These were questions of detail, not questions of foundation. The foundation, everyone agreed, was solid. A few theorists, mostly those working on the margins of the standard model, quietly hoped that Webb might find something genuinely unexpected. Every major new telescope in the history of astronomy had produced at least one surprise, but the mainstream expectation was confirmation. The universe, as described by Lambda-CDM and measured by Planck, was understood. Webb would sharpen the resolution, fill in the blanks, and cement the concordance for a generation. That was the plan. That was the confidence. And that confidence was not arrogance. It was earned. Earned by decades of successful predictions. Earned by Planck's extraordinary precision. Earned by the convergence of independent measurements on the same coherent picture. Scientists prepared their observation programs. The Cepheid variable star campaigns would sharpen the distance ladder and help resolve a nagging disagreement about the expansion rate. The deep field surveys would peer into the first few 100 million years after the Big Bang, searching for the earliest galaxies. The spectroscopic programs would analyze the chemical composition of objects so distant that their light had been traveling since before the Earth, the Sun, and every star you can see in the night sky had formed. The plans were meticulous, the expectations were measured. The telescope would refine the model, confirm the predictions, and fill in the few remaining blanks in the concordance picture that Planck and Hubble and 2 decades of surveys had constructed. That is not what happened. Within the first year of observations, results began arriving that did not fit. Galaxies appeared at distances where the model said they should not yet exist in such sizes. The expansion rate measurements came in with numbers that deepened a discrepancy instead of resolving it. Objects emerged from the ancient universe with properties that the simulations had not predicted and the framework struggled to explain. None of these findings, taken alone, was enough to topple a model that had survived 25 years of testing. But taken together, they traced a pattern. They pointed, consistently and from independent directions, toward the same uncomfortable conclusion. The standard model of cosmology is not wrong. It is magnificent. It explains more about the universe, with greater precision, than any framework that came before it. But it may not be complete. There may be something it is missing. And James Webb, with its golden mirror and its infrared eyes, and its position 1,000,000 miles from Earth, may be the first instrument precise enough to see exactly where the incompleteness lies. The question is what exactly Webb found. And the answer begins with a number. A single number measured 2 different ways, producing 2 different answers, with a gap between them that the most successful model in the history of cosmology cannot close. That number is the Hubble constant, and the story of its crisis is next. There is a particular kind of scientific problem that keeps physicists awake at night. It is not the kind where you have no answer. That is frustrating, but manageable. The truly disturbing kind is when you have 2 answers, both measured carefully, both checked repeatedly, both supported by independent methods, and they disagree. The Hubble constant is that kind of problem, and James Webb did not solve it. Webb made it worse. To understand why, you need to understand what the Hubble constant actually measures and why getting its value right matters so profoundly for everything else in cosmology. The Hubble constant, abbreviated H0, quantifies how fast the universe is expanding right now. Its units are kilometers per second per megaparsec. That sounds technical, but the meaning is simple. For every megaparsec of distance between you and a distant galaxy, a megaparsec being roughly 3.26 million light-years, that galaxy appears to be receding from you at a certain number of kilometers per siding megaparsec. Second, the Hubble constant tells you what that number is. If H0 is larger, the universe is expanding faster. If it is smaller, the expansion is slower. And that single number is not just a curiosity about cosmic velocity. It feeds directly into calculations of the age of the universe, the distances to faraway objects, the density of dark energy, the timeline of structure formation, and ultimately the fate of everything that exists. Get H0 wrong, and the entire cosmic picture shifts. For most of the 20th century, measuring the Hubble constant was one of the great ongoing struggles of astronomy. The difficulty is that you need 2 things simultaneously: the distance to a galaxy and its recession velocity. Velocity is the easy part. You measure the redshift of light from the galaxy. As space expands, the wavelength of light traveling through it gets stretched toward the red end of the spectrum. The amount of stretching tells you how fast the galaxy is moving away. That measurement is precise and well understood. Distance is the hard part. The universe does not come with a tape measure. You cannot point a laser at a galaxy 300 million light-years away and wait for the beam to bounce back. Instead, astronomers use a method that sounds almost elegant in principle and becomes nightmarishly complex in practice. It is called the cosmic distance ladder. The idea is this: you start with objects whose true brightness you know. If you know how bright something actually is, and you measure how bright it appears from Earth, the difference tells you how far away it is. A candle that you know emits 100 watts, but appears as faint as a 1-watt bulb, must be a certain calculable distance away. The same logic applies to stars. The first rung of the ladder uses objects relatively close to us, stars whose distances can be measured directly using parallax, the tiny shift in a star's apparent position as the Earth moves from one side of its orbit to the other. This works for stars within a few thousand light-years. It gives you an anchor, a set of distances you can trust absolutely because they are based on simple geometry. The second rung uses a special class of stars called Cepheid variables. These are pulsating stars whose brightness rises and falls in a regular cycle. In 1912, astronomer Henrietta Swan Leavitt discovered a remarkable relationship between the period of a Cepheid's pulsation and its intrinsic luminosity. A Cepheid that pulses slowly is genuinely brighter than one that pulses quickly. Measure the period, and you know the true brightness. Compare the true brightness to the apparent brightness, and you know the distance. Cepheids are bright enough to be seen in galaxies tens of millions of light-years away. They extend the ladder far beyond the reach of parallax. Edwin Hubble himself used Cepheids to prove that distant nebulae were separate galaxies. And for nearly a century, they have remained one of the most important tools in observational cosmology. But Cepheids are not simple objects. They are complex stars, and using them as distance markers requires correcting for several complicating factors. Their brightness depends not only on their pulsation period, but also on their chemical composition specifically, their abundance of elements heavier than hydrogen and helium, which astronomers call metallicity. A Cepheid in a metal-rich galaxy pulsates at a slightly different brightness than an identical period Cepheid in a metal-poor galaxy. That difference must be calibrated out. Cepheids also tend to be young stars, which means they live in the crowded, dusty spiral arms and inner disks of galaxies. Interstellar dust dims the light passing through it, and if the amount of dust is not correctly estimated, the Cepheid appears fainter than it should, and its distance is overestimated. Each of these corrections introduces an opportunity for subtle error, and each has been debated for decades. The third rung uses type Ia supernovae. These explosions occur in binary star systems when a white dwarf accumulates enough material from a companion star to trigger a thermonuclear detonation. The physics of the explosion is consistent enough that every type Ia supernova reaches roughly the same peak brightness. They are extraordinarily luminous, bright enough to be seen across billions of light-years. By calibrating their true brightness, using Cepheids in the same host galaxies, astronomers can extend the distance ladder deep into the cosmos and trace the expansion history of the universe across most of its lifetime. Each rung depends on the one below it. Parallax calibrates the Cepheids. Cepheids calibrate the supernovae. And the supernovae reach far enough to map the expansion rate with precision. It is a chain, and every link must be solid. If any rung contains an error, a bias in the Cepheid brightness, a miscalibration in the supernova standard, the error propagates upward through every subsequent measurement. This is why the Hubble constant was uncertain by a factor of 2 for decades. The ladder was shaky. Different astronomers using different calibrations got different answers, ranging from roughly 50 to roughly 100 kilometers per second per megaparsec. It was an embarrassment for a field that claimed to study the entire universe. By the early 2000s, the situation had improved dramatically. Hubble Space Telescope observations of Cepheids in dozens of galaxies tightened the measurements. The Hubble Key project, led by Wendy Friedman, published a landmark value of 72 kilometers per second per megaparsec in 2001, with an uncertainty of about 10%. The field was converging. Then Planck changed the game entirely. As we discussed, the Planck satellite mapped the cosmic microwave background with extraordinary precision. But Planck did more than photograph the afterglow of the Big Bang. It measured the contents and geometry of the early universe so accurately that scientists could use Lambda-CDM to calculate what the Hubble constant should be today, based entirely on conditions 380,000 years after the Big Bang. This point deserves careful attention, because everything that follows depends on understanding exactly what Planck's number represents and how it differs from the distance ladder measurement. Planck does not measure the current expansion rate of the Planck's number universe. It cannot. The cosmic microwave background was released when the universe was 380,000 years old. That light tells you about conditions at that epoch, the density of matter, the density of radiation, the geometry of space, the amplitude of the density fluctuations that would eventually become galaxies. It is a snapshot of the infant universe, frozen in light. To get from that infant snapshot to a prediction about the expansion rate today, you need a bridge. That bridge is the standard cosmological model Lambda-CDM. The model takes the conditions Planck measured and runs them forward through 13.8 billion years of cosmic evolution. It calculates how the universe expanded through its radiation-dominated era, its matter-dominated era, and its current dark energy-dominated era. It accounts for every transition, every shift in the balance of energy between matter, radiation, and dark energy. And at the end of that calculation, it produces a prediction for what the Hubble constant should be right now. That prediction is 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. Here is what makes this so powerful and so dangerous at the same time. The prediction is extraordinarily precise because Planck's measurements of the early universe are extraordinarily precise. But the prediction is only as reliable as the model used to make it. If Lambda-CDM correctly describes every phase of the universe's expansion from 380,000 years after the Big Bang to the present day, then the prediction is trustworthy. If the model is missing something, some process, some force, some phase of expansion that it does not account for, then the prediction will be wrong, and it will be wrong in a very specific way. It will disagree with a direct measurement of the expansion rate made in the local universe today. That is exactly what happens. The most prominent distance ladder measurement comes from the SH0ES team, led by Adam Rees at Johns Hopkins University, using Hubble Space Telescope observations of Cepheids in over 40 galaxies, calibrated against geometric distance anchors and connected to Type Ia supernovae reaching deep into the expanding universe. The SH0ES team has consistently measured a value of approximately 73 kilometers per second per megaparsec, also with an uncertainty of around 1%. 67 versus 73. Both measurements are precise. Both have been checked extensively. And they do not agree. This is the Hubble tension. To feel the weight of this discrepancy, consider what it means in practice. If Planck's prediction is correct, the universe is approximately 13.8 billion years old. If the SH0ES measurement is correct instead, the universe is younger, closer to 13.2 or 13.3 billion years. That is a difference of 500 million years. 500 million years of cosmic history, gained or lost depending on which number is right. The size of the observable universe changes. The distances to every galaxy beyond our immediate neighborhood shift. The density of dark energy required to explain the acceleration adjusts. The timeline on which the first stars and galaxies formed contracts. One number Hazro, and the entire cosmic picture recalibrates around it. At first, most scientists assumed the discrepancy would go away. The history of cosmology is littered with measurement discrepancies that turned out to be systematic errors, miscalibrated instruments, unaccounted for dust, subtle biases in data analysis. The natural expectation was that either Planck's model-dependent prediction contained a flaw, or the distance ladder contained a hidden source of error. Someone had made a mistake, and with better data, the mistake would be found and the numbers would converge. That expectation was reasonable. It was also, as it turned out, wrong. Year after year, both measurements were refined, cross-checked, and scrutinized by independent teams. The distance ladder value held steady. The Planck value held steady. The gap did not close. By the early 2020s, the statistical significance of the disagreement had grown to roughly 5 sigma, meaning the probability of the discrepancy being a random fluke was approximately 1 in 3.5 million. In physics, 5 sigma is traditionally the threshold for claiming a discovery. The Hubble tension had crossed that threshold. Whatever was causing the disagreement, it was almost certainly real. And that is where James Webb entered the story. Not as a revolutionary, but as a referee. One of the most persistent criticisms of the distance ladder measurement was that Hubble Space Telescope's resolution, while extraordinary, might not be sufficient to cleanly separate Cepheid variables from nearby stars in crowded galactic environments. If the light of a Cepheid was blended with the light of surrounding stars, a phenomenon called crowding the Cepheid would appear brighter than it truly was, and the distance to its host galaxy would be underestimated. Underestimate the distances, and the expansion rate you calculate comes out too high. This was not a speculative concern. Cepheids, as young massive stars, live in the dense inner regions of spiral galaxies where stellar populations are tightly packed. At the distances the SH0ES team was observing tens of millions of light-years, even Hubble's formidable resolution could not always cleanly separate a Cepheid from its neighbors. If even a small amount of unresolved starlight was leaking into the Cepheid measurements across many galaxies, the cumulative effect could bias the Hubble constant upward by exactly the amount needed to create the tension. Webb's infrared instruments have roughly 4 times the angular resolution of Hubble in the relevant wavelengths. Where Hubble saw a blur, Webb could resolve individual stars. If crowding was inflating the Cepheid brightnesses, Webb would see it immediately. In 2023, the SH0ES team published their first Webb observations of Cepheids. The results were unambiguous. Webb confirmed Hubble's measurements. The Cepheid brightnesses measured by Webb matched those measured by Hubble within the expected uncertainties. The stars that Hubble had identified as Cepheids were indeed Cepheids. Their brightnesses were not significantly contaminated by crowding. The distance ladder was not broken. Adam Rees stated the conclusion directly. With measurement errors negated, what remains is the real and exciting possibility that we have fundamentally misunderstood the universe. By 2024, the SH0ES team had extended their Webb observations across the full range of galaxies that Hubble had studied, spanning distances out to roughly 130 million light-years. The result held. The local expansion rate remained near 73. Hubble's measurements were vindicated, and the most commonly proposed source of systematic error, stellar crowding, was effectively ruled out with very high confidence. But the story has a complication. And the complication carries the name of the same astronomer who helped tighten the Hubble constant 2 decades earlier. Wendy Friedman, now at the University of Chicago, leads the Chicago Carnegie Hubble program. Her team has taken a different approach to the distance ladder, one that deliberately avoids Cepheids altogether for part of the analysis. Instead, Friedman's team uses 2 alternative distance indicators. The first is the tip of the red giant branch method. The technique exploits a well-understood feature in the life cycle of old, low-mass stars. As a red giant star evolves, it ascends a predictable track on a brightness diagram, growing steadily more luminous. Then, at a specific point, helium fusion ignites in its core in a sudden event called the helium flash, and the star abruptly drops in brightness and moves to a different evolutionary phase. The brightness at which this transition occurs, the tip of the red giant branch, is remarkably consistent from star to star and from galaxy to galaxy. It acts as a standard candle, much like a Cepheid, but with different strengths and different vulnerabilities. Red giants are old stars. They do not live in dusty spiral arms. They are found in the clean, sparse halos and outskirts of galaxies, where crowding is less of a problem and dust absorption is minimal. In principle, they should provide a cleaner distance measurement than Cepheids in certain environments. The second indicator Friedman's team uses is a class of carbon-rich, asymptotic giant branch stars, sometimes called J-region asymptotic giant branch stars. These are evolved stars that occupy a particular region of the infrared color magnitude diagram. Their intrinsic brightness in the near-infrared J-band is tightly constrained, making them another independent standard candle. Webb's infrared capabilities are particularly well suited to observing these stars, because the J-band falls squarely within the wavelengths where the telescope achieves its sharpest resolution and highest sensitivity. In 2024, Friedman published preliminary Webb results suggesting that these alternative methods gave a lower value for the Hubble constant, closer to 70. Possibly consistent with Planck's 67.4 within the uncertainties. By May 2025, her team published an expanded analysis in the Astrophysical Journal, using Webb and Hubble data on 11 galaxies and reporting a value of 70.4 kilometers per second per megaparsec, with an uncertainty of roughly 3%. 70.4 sits between Planck's 67.4 and SH0ES's 73. With a 3% uncertainty, its error bars overlap with both. If Friedman is right, the Hubble tension might not be a crack in the model at all. It might be a measurement problem with Cepheids not crowding, but something more subtle in how their brightnesses are calibrated, corrected for dust, or adjusted for chemical composition differences across galaxies. Friedman herself has pointed to the complexity of Cepheid calibration as a persistent concern. Different assumptions about how metallicity affects Cepheid luminosity can shift the resulting Hubble constant by several kilometers per second per megaparsec, enough to close or widen the tension depending on which correction is applied. The reaction from the broader community was immediate and divided. Dan Skolnick, an astrophysicist at Duke University who works on supernova cosmology, publicly disagreed with Friedman's interpretation. At a meeting of the American Astronomical Society in January 2025, Skolnick declared the Hubble tension was now a crisis. He noted that Friedman's team excluded certain supernovae from their sample that other groups would have included, and that the tip of the red giant branch method carries its own calibration uncertainties that are not yet fully resolved. The precise brightness of the tip depends on the stellar population being observed, its age, its metallicity, the photometric system used to measure it, and different research groups have reached different conclusions about exactly where the tip falls. These are not trivial differences. They propagate through the distance ladder with the same relentless logic that makes the Cepheid calibration so consequential. Other researchers have pointed out that Friedman's value of 70.4, while lower than the SH0 value, is still higher than Planck's 67.4. The gap is reduced, but not eliminated. And as Friedman's own uncertainties shrink with additional Webb data, the question of whether her error bars continue to overlap with Planck will become increasingly decisive. A 3% uncertainty is large by the standards of modern precision cosmology. If it tightens to 2% or 1%, and the central value remains near 70, the tension with Planck persists smaller than the SH0 version, but real. The scientific community is now in one of the most uncomfortable positions a field can occupy. Two highly credible teams, both using the most powerful space telescope ever built, are arriving at different answers to the same question. Rees and SH0 insist the local expansion rate is near 73 and that Webb's data confirm it. Friedman and the Chicago Carnegie team argue the true value may be closer to 70 and that the tension with Planck is less severe than it appears. This is not a dispute between fringe researchers and mainstream science. It is a dispute between two of the most respected measurement teams in observational cosmology, both armed with Webb data, both publishing in the top journals, both defending their methods with detailed statistical analyses. The resolution will not come from rhetoric. It will come from additional data, independent methods, and the slow grinding machinery of scientific cross-verification. And in December 2025, another player entered the field, one that sidesteps the entire distance ladder debate. The TD Cosmo collaboration published results using an entirely different method for measuring the Hubble constant, one that does not rely on Cepheids, red giants, supernovae, or any rung of the traditional cosmic distance ladder. Their approach uses strongly lensed quasars. The technique is called time delay cosmography, and it works through a principle that sounds almost like science fiction, but is grounded firmly in general relativity. When a massive galaxy sits between Earth and a distant quasar, one of the brightest objects in the universe, powered by a supermassive black hole consuming enormous quantities of gas, the galaxy's gravity warps the fabric of space-time around it. The quasar's light, instead of traveling in a straight line, follows curved paths around the lensing galaxy. If the alignment is close enough, the light splits into multiple images of the same quasar, each following a different curved path through the gravitational field. Here is the crucial detail. Because each path has a different length and passes through a different region of curved space-time, the light from each image arrives at Earth at a slightly different time. Quasars are variable objects. Their brightness flickers as the accretion disk around the central black hole fluctuates. By monitoring those brightness fluctuations in each lensed image, astronomers can measure the time delay between them. One image might brighten 3 weeks before another because its light traveled a shorter path. That time delay, combined with a careful model of the lensing galaxy's mass distribution, allows astronomers to calculate the absolute distance to the lens system, and from the distance and the redshift, they can derive the Hubble constant. The entire measurement is geometric. It depends on the curvature of space-time, the speed of light, and the properties of the gravitational lens. It does not depend on the brightness of any star. It does not depend on any rung of any ladder. For 6 of their 8 lens systems, the TD Cosmo team used stellar velocity data from Webb's NIRSPEC instrument to improve their models of the lensing galaxies. The way stars move inside a galaxy reflects how mass is distributed within it. By measuring those velocities with Webb's spectroscopic precision, the team could constrain the mass models more tightly, reducing one of the largest sources of uncertainty in the technique. The fact that the exact distribution of mass in the lensing galaxy is not known a priori and must be inferred. Their result supported the higher end of the Hubble constant, closer to the SH0 value than to Planck. They described the finding as further confirmation that the Hubble tension is real and not an artifact of the distance ladder. Frédéric Courbet, one of the collaboration's lead researchers, emphasized that the lensing time delay method is fully independent of any other method and does not involve complicated calibrations, a pointed contrast with the ongoing debate between Cepheids and red giants. This is the current state of affairs. 3 independent methods: Cepheid calibrated supernovae, tip of the red giant branch calibration, and gravitational lensing. Time delays are producing results that cluster in the range of roughly 69 to 73, while the Planck prediction from the early universe remains stubbornly fixed near 67. The distance ladder values and the lensing value sit above the Planck value. Friedmann's value sits in the middle, possibly bridging the gap or possibly reflecting a calibration difference that has not yet been identified. Here is what matters for our story. Even in the most optimistic reading, even if Friedmann's lower value is correct and the tension with Planck is reduced, a gap remains. 70.4 is still higher than 67.4. The error bars overlap only because Friedmann's uncertainties are larger than Planck's. As those uncertainties shrink with future observations, the overlap may disappear. And if it does, the tension returns in full force. Now, step back and ask what the tension actually means, physically, if it is real. Planck's value of 67.4 is not a measurement of the current expansion rate. It is a prediction, derived by taking conditions measured in the early universe and running them forward through 13.8 billion years of cosmic evolution using Lambda-CDM. The prediction assumes that the model correctly describes everything that happened in between every phase of expansion, every transition in the dominant form of energy, every interaction between dark matter, dark energy, ordinary matter, and radiation. The distance ladder measures the expansion rate directly, today, without assuming any cosmological model. It simply measures distances and velocities, and divides one by the other. The lensing method does the same, measures a geometric quantity in the local universe without relying on the model to bridge from the past. If both the direct measurements and the model's prediction were correct, they would agree. They do not. And the disagreement points to a specific location in cosmic history, not to the early universe, where Planck's measurements are extraordinarily precise and well tested, not to the local universe, where the distance ladder and lensing measurements operate, but to the vast stretch of time in between. Somewhere in the 13 billion years of expansion that connects the cosmic microwave background to the present day, something happened that Lambda-CDM does not account for. Some process, some force, some phase of cosmic history that the model either describes incorrectly or misses entirely. That is not a small statement. Lambda-CDM has been tested against an enormous range of observations spanning most of cosmic history. If something in that history deviates from the model's predictions, it represents a genuine gap in our understanding of how the universe evolved, and the Hubble tension, if real, points precisely to where that gap lies, somewhere in the billions of years between the release of the cosmic microwave background and the present day. Theorists have proposed dozens of ideas for what might fill the gap. The most discussed is early dark energy, a hypothetical form of dark energy that existed briefly in the first few 100,000 years after the Big Bang boosted the expansion rate during that epoch and then disappeared. If such a component existed, it would change the sound horizon, the characteristic size of the density fluctuations imprinted in the cosmic microwave background in a way that shifts Planck's prediction upward, potentially closing the gap. Other proposals include modifications to the number or behavior of neutrinos in the early universe, interactions between dark matter and dark energy, a time-varying gravitational constant, or more exotic modifications to general relativity at cosmological scales. None of these proposals has gained consensus. None has been confirmed by independent evidence. And none has succeeded in resolving the Hubble tension without creating new problems elsewhere in the cosmological framework. That is the hallmark of a genuine crisis in physics. The data are clean. The discrepancy is statistically significant, and no simple fix works without breaking something else. Rees himself captured the situation with a metaphor that has become widely cited. He described it as though the distance ladder has firmly set an anchor point on one shoreline of a river, and the cosmic microwave background has firmly set another anchor on the opposite shore. How the universe's expansion was changing in the billions of years between those two endpoints has yet to be directly observed. We need to find out if we are missing something on how to connect the beginning of the universe and the present day. That missing connection is the crack, not in the data, but in the model. The data on both sides are solid. It is the bridge between them, the Lambda-CDM description of cosmic evolution, that may be incomplete. And here is the part that makes the Hubble tension more than just a measurement puzzle. If Lambda-CDM is missing a component of the expansion history, even a small one, it means the model's extraordinary success was partly hiding a flaw. The reason is that the cosmic microwave background constrains a combination of cosmological parameters, not each parameter individually. A small error in one parameter can be compensated by a small shift in another, keeping the overall fit looking perfect while the underlying physics drifts subtly away from reality. The Hubble tension may be the first place where that hidden compensation fails, where the error can no longer be absorbed, where the crack finally becomes visible. It is not the only place, because while the Hubble tension was building from a curiosity into a crisis, Webb was simultaneously discovering something else, objects in the early universe that the standard model did not predict, structures that should not have had time to form, and evidence from an entirely independent experiment suggesting that the most fundamental assumption of Lambda-CDM, the constancy of dark energy, may itself be wrong. The Hubble tension opened the crack. What comes next widens it. When the James Webb Space Telescope pointed its mirror towards seemingly empty patches of sky and collected light that had been traveling for more than 13 billion years, astronomers expected to find the universe in its infancy, small clumps of gas just beginning to collapse, faint proto-galaxies stumbling through their first attempts at star formation. The cosmic equivalent of watching a newborn take its first uncertain breath. What they found instead looked more like a teenager who had somehow skipped childhood entirely. Within the first year of Webb's science, operations, deep field surveys, began returning images of galaxies at redshifts of 7, 8, 9, and beyond, corresponding to a period when the universe was less than 700 million years old, in some cases less than 400 million years after the Big Bang. The objects were not faint, uncertain smudges at the edge of detection. They were bright. They were structured. And when astronomers estimated their stellar masses using the standard techniques of spectral energy distribution fitting, the numbers were staggering. Some of these galaxies appeared to contain tens of billions of solar masses in stars. A few candidates pushed past 100 billion, rivaling the stellar mass of the Milky Way. a galaxy that has had 13 billion years to grow. These ancient systems had apparently accomplished in a few 100 million years what our own galaxy took more than 20 times longer to achieve. The reaction in the astronomical community was immediate and intense. Astrophysicist Erica Nelson, part of the team that identified 6 of the most massive early candidates, described them as universe breakers. The term was informal, but the concern behind it was serious. Lambda-CDM does not merely predict that galaxies grow slowly in the early universe, it requires it. The model specifies how dark matter halos form and merge over cosmic time, how baryonic gas falls into those halos, and how efficiently that gas converts into stars. At every step, there are physical limits. Dark matter halos in the early universe can only grow so large, so quickly, because the density fluctuations from which they formed were small, imprinted in the cosmic microwave background at a level of roughly 1 part in 100,000. Gravity amplifies those fluctuations over time, but the amplification takes time. A halo massive enough to host a Milky Way-scale galaxy simply should not exist in the quantities Webb was finding within the first billion years. Even if the halos were present, the baryonic physics imposes its own ceiling. Gas falling into a dark matter halo heats up through gravitational compression. Before it can form stars, it needs to cool, and cooling takes time. Feedback processes, radiation pressure from young stars, shock waves from supernovae, energy output from growing black holes blow gas out of galaxies and suppress further star formation. In the standard picture, these feedback mechanisms ensure that galaxies convert only a fraction of their available gas into stars at any given time. Typical conversion efficiencies in simulations run around 10 to 20% of available baryons. The galaxies Webb was finding seemed to demand efficiencies of 50% or higher. Some of the most extreme candidates implied baryon to stellar mass conversion rates above 80%, meaning nearly every atom of hydrogen and helium that fell into the dark matter halo had been turned into a star. That is not just unusual. In the context of standard galaxy formation theory, it borders on physically implausible. A study published in Nature Astronomy in 2023 by Michael Boylan-Colchin at the University of Texas examined the problem rigorously. He calculated the maximum stellar mass density that Lambda-CDM allows at high redshift by taking the known dark matter halo mass function, the predicted number of halos at each mass, and assuming that every single baryon in every halo was converted into stars with perfect efficiency. Even under that extreme and unrealistic assumption, the most massive galaxy candidates, reported by Webb, sat at the very edge of what the model permits. For more realistic star formation efficiencies, the observed masses exceeded what Lambda-CDM could produce. The implication was unsettling. Either the masses were being overestimated, or the standard model was underestimating how quickly structures formed in the early universe. Both possibilities carried consequences. The scientific community responded with exactly the kind of disciplined skepticism that a claim of this magnitude demands. And within 2 years, the picture had shifted significantly. In November 2025, a study led by University of Texas graduate student Katherine Swarowski, published in the Astronomical Journal, provided an important correction. Swarowski's team performed detailed spectroscopic follow-up of early galaxy candidates using Webb data and found that a significant fraction of the objects originally flagged as impossibly massive galaxies were not what they appeared to be. The problem was active galactic nuclei, supermassive black holes at the centers of these young galaxies, violently consuming surrounding gas and radiating enormous amounts of energy across the electromagnetic spectrum. When an active galactic nucleus contributes a large fraction of a galaxy's total light, the standard method of estimating stellar mass, which assumes the light comes primarily from stars, overestimates the mass dramatically. The galaxy looks brighter than its stars alone would make it, and the analysis interprets that excess brightness as more stars rather than as a central engine powered by accretion onto a black hole. When Swarovski's team accounted for the contribution of active galactic nuclei, many of the most extreme mass estimates dropped significantly. Some of the so-called universe breakers turned out to be much less massive than originally believed. Stephen Finkelstein, a co-author on the study, stated the conclusion bluntly: "There is no crisis in terms of the standard model of cosmology. Any time you have a theory that has stood the test of time for so long, you have to have overwhelming evidence to really throw it out, and that is simply not the case. That would seem to close the book." The impossible galaxies were not impossible after all. The model survives. But the book does not close cleanly. Even after correcting for active galactic nuclei, Swarovski's analysis found that there are still roughly twice as many massive galaxies in Webb's early universe data as the standard model predicts. The most extreme outliers were explained away. The population-level excess was not. Something in the early universe was producing massive galaxies more efficiently than simulations anticipated. And the revised estimates still sat uncomfortably above the model's expectations. This is the kind of discrepancy that does not generate dramatic headlines, but keeps theorists working late into the night. It is not a crisis, it is a pressure. A persistent, quantifiable pressure on the galaxy formation models embedded within Lambda-CDM, coming from the one direction the models had the least observational constraint, the first billion years of cosmic history. Separate from Swarovski's work, a team led by Mengyuan Xiao published results in Nature in late 2024, identifying what they called ultra-massive red monsters galaxies at high redshift that had converted far more of their available gas into stars than any simulation had predicted. Their analysis confirmed that even when active galactic nuclei were accounted for, these galaxies represented a genuine challenge to standard galaxy formation models. The baryonic conversion efficiency required to explain them pushed well above the 20% typical of simulations. Then, in 1965, two radio engineers at Bell Telephone Laboratories in New Jersey accidentally settled the argument. Arno Penzias and Robert Wilson were calibrating a large horn-shaped antenna originally built for satellite communication. No matter what they did, they could not eliminate a faint, persistent hiss from their signal. They checked the equipment. They rebuilt connections. They famously cleaned pigeon droppings from inside the antenna, thinking the birds might be the source. Nothing worked. The noise was always there, coming from every direction in the sky equally, day and night, regardless of where they pointed the instrument. What they had stumbled into was the afterglow of creation, the cosmic microwave background radiation. The red monsters did not violate the absolute cosmological limits set by the dark matter halo mass function. They did not break Lambda-CDM at the level of fundamental cosmology. But they broke the astrophysical models that operate within that framework, the detailed prescriptions for how gas cools, how stars form, how feedback operates, and how quickly a galaxy can assemble its stellar population. Those prescriptions are not peripheral decorations on the standard model. They are the machinery that connects the model's cosmological predictions to the observable universe. If the machinery is wrong in the early universe, the implications ripple outward through every prediction that depends on it. Researchers at Cambridge, studying over 250 galaxies from the JADE survey using Webb, found that early galaxies were overwhelmingly chaotic, turbulent, gas-filled systems with irregular motions, nothing like the orderly rotating disks that had been tentatively suggested by earlier, lower-resolution observations. The chaos itself was not the surprise. The surprise was the sheer efficiency with which these disordered systems were forming stars. Even in their turbulence, they were building stellar mass at rates that the models underestimated. The early galaxy problem has not destroyed the Standard Model, but it has revealed a weakness in a specific and important area, the transition from cosmological initial conditions to the astrophysical structures we observe. Webb has shown that whatever happened in the first few 100 million years after the Big Bang was messier, faster, and more productive than the simulations predicted. The model's cosmological skeleton may be sound, but its astrophysical muscles need rebuilding. And the question that lingers is whether rebuilding the muscles will be enough, or whether the skeleton itself will need adjustment. It is worth pausing here to note a subtle but critical distinction that runs through the entire early galaxy debate. There are two levels at which the Standard Model can be challenged. The first is the cosmological level, the fundamental parameters of Lambda-CDM, the density of dark matter, the nature of dark energy, the expansion history of the universe. The second is the astrophysical level, the detailed models of how gas, stars, and black holes behave within the scaffolding that Lambda-CDM provides. The early galaxy excess, as currently understood, lies primarily at the second level. The galaxies are not so massive that they violate the total amount of matter Lambda-CDM says should exist. They are so massive that the processes by which matter was supposed to assemble into galaxies were clearly more efficient than anyone modeled. That is an astrophysics problem, not a cosmology problem, at least for now. But the boundary between astrophysics and cosmology is not a clean line. If the astrophysical models need to be revised dramatically enough, the revisions can feed back into the cosmological parameters. If star formation was far more efficient in the early universe, the feedback from those stars, radiation, outflows, chemical enrichment would have altered the intergalactic medium in ways that affect the growth of subsequent structures. If supermassive black holes formed earlier and grew faster than expected, their energy output could have heated surrounding gas and influenced the clustering of matter on scales large enough to register in cosmological measurements. The ripple effects are difficult to calculate, and their ultimate reach is unknown. What can be said is that a factor of 2 discrepancy in the predicted number of massive early galaxies is not a problem that stays neatly contained. It spreads. That question became considerably more urgent in March 2025, when an entirely different experiment delivered results that struck at the very heart of Lambda-CDM from a completely independent direction. Not from the early galaxy population, not from the distance ladder, but from the large-scale distribution of galaxies across 11 billion years of cosmic history. The dark energy spectroscopic instrument, known as DESI, is not a space telescope. It is a ground-based instrument mounted on the Nicholas U. Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona. Its purpose is singular and ambitious: to create the largest 3-dimensional map of the universe ever made by measuring the spectra of tens of millions of galaxies and quasars, each spectrum providing a precise distance through its redshift. DESI accomplishes this using 5,000 robotic fiber positioners that can simultaneously capture light from 5,000 different objects across a wide field of view. Each night, it gathers more galaxy spectra than most previous surveys collected in their entire operational lifetimes. By the time of its second major data release in March 2025, DESI had measured nearly 15 million galaxies and quasars spanning the last 11 billion years of cosmic history. The scientific goal is to measure baryon acoustic oscillations. That term requires unpacking, because the measurement technique behind it is one of the most elegant in all of cosmology. And understanding it is essential to grasping why the DESI results carry the weight they do. In the very early universe, before the cosmic microwave background was released, the cosmos was a single blinding fog. Matter and radiation were locked together in a hot, dense plasma, a seething mixture of protons, electrons, and photons, all interacting furiously. Within that plasma, sound waves propagated. Not sound in the sense of vibrations through air, but pressure waves, disturbances in density that traveled outward from regions where matter was slightly more concentrated than average. The physics is the same. A region of higher density compresses the surrounding material, which pushes back, creating an oscillating wave that radiates outward at a calculable speed, close to 60% of the speed of light, through the conditions of the early plasma. These sound waves traveled for 380,000 years, from the moment the universe became hot enough to sustain them until the moment it cooled enough for atoms to form and photons to decouple from matter. At that instant, the waves froze. The pressure that had been driving them vanished as the photons escaped into what would become the cosmic microwave background. The matter, suddenly free from radiation pressure, was left in a specific configuration, a characteristic shell of slightly higher density surrounding each original overdense point, with a radius equal to the distance the sound wave had traveled before freezing. That distance is called the sound horizon, and it is approximately 490 million light-years in today's expanded universe. That shell left a permanent mark. In the millions and billions of years that followed, gravity amplified the density fluctuations, pulling matter together to form galaxies and galaxy clusters. But the imprint of the original sound waves persisted. Galaxies are slightly more likely to be found separated by the sound horizon distance than by any other distance. It is a subtle statistical preference, detectable only in surveys large enough to map millions of galaxies. But it is there, a preferred spacing, a cosmic ruler baked into the distribution of matter by the sound waves of the infant universe. Baryon acoustic oscillations are that ruler. And the power of the measurement lies in the fact that the ruler has a known physical size, calculable from the physics of the early universe. If you measure how large the ruler appears at different distances, different redshifts, you can determine how much space has expanded between then and now. Do this at multiple redshifts, and you trace the expansion history of the universe across billions of years. That expansion history is directly sensitive to the properties of dark energy, because dark energy's influence on the expansion rate has changed over time as it became the dominant component of the universe's energy budget. In Lambda-CDM, dark energy is a cosmological constant. Its energy density does not change as the universe expands. A cubic meter of empty space today contains exactly the same amount of dark energy as a cubic meter of empty space a billion years ago or a billion years from now. This constancy is the lambda in Lambda-CDM. It is the simplest possible description of dark energy, and for 2 decades it fit every observation. DESI's results suggest it may not be that simple. When the DESI team analyzed their baryon acoustic oscillation measurements alone, the data were consistent with a cosmological constant. Lambda-CDM survived in isolation. But when DESI's data were combined with measurements from the cosmic microwave background and from Type Ia supernovae, a different picture emerged. The standard model struggled to explain all the observations simultaneously. A model in which dark energy's influence changes over time specifically, one in which dark energy was stronger in the past and is weakening as the universe ages, provided a better fit to the combined data. The statistical significance of this preference varied depending on which supernova dataset was. used in the combination. With some datasets, the preference for evolving dark energy reached between 3 and 4 sigma. With others, it was weaker. The result had not crossed the 5 sigma threshold required for a formal discovery. But it was far too strong to dismiss as a statistical fluctuation, especially because the same trend had appeared in DESI's earlier first-year data release in April 2024, and the second data release, using more than double the data, strengthened it. Willem Elbers, a postdoctoral researcher at Durham University and co-chair of DESI's Parameter Estimation Working Group, summarized the situation with notable precision. For a couple of decades, we have had this standard model of cosmology that is really impressive. As our data are getting more and more precise, we are finding potential cracks in the model and realizing we may need something new to explain all the results together. The word he used, cracks, was not rhetorical. It was diagnostic. To understand what evolving dark energy means for the standard model, consider what the cosmological constant actually represents. In Lambda-CDM, dark energy is identified with the energy of the quantum vacuum, the baseline energy that empty space possesses, even in the absence of any matter or radiation. Quantum field theory predicts that this vacuum energy should exist, and the cosmological constant assigns it a fixed value. That value carries the deep theoretical discomfort we encountered earlier. No one knows why it takes the specific number it does, but, whatever its origin, it was assumed to be constant. It was built into the architecture of the model as a fixed parameter, not a variable. If dark energy is not constant, if its equation of state varies with time, then it is not vacuum energy in the simple sense. It is something else, a dynamic field, perhaps, evolving as the universe ages. Theorists have names for such fields: quintessence, thawing dark energy, phantom energy, depending on the mathematical form of the variation. Each carries different implications for the past and future of the cosmos, a dark energy that was stronger in the past and is weakening over time. The trend DESI's data seem to favor would mean the expansion of the 2025-2000. The universe was being driven harder at earlier times and is now gradually relaxing. That has consequences for the Hubble tension. A different expansion history changes the relationship between early universe conditions and the present-day expansion rate. It is not yet clear whether evolving dark energy of the type DESI sees could resolve the Hubble tension, but several theoretical groups are actively investigating the possibility. In March 2026, a team at the Chinese Academy of Sciences, led by Yun Chen, published a framework in the Astrophysical Journal attempting to address both the DESI signal and the Hubble tension within a single unified model of evolving dark energy. Indication that the community is beginning to treat these tensions not as separate puzzles, but as potentially related symptoms of the same underlying incompleteness. There is a further complication that deserves careful attention. Not everyone agrees that the DESI results point to evolving dark energy. George Efstathiou at the University of Cambridge published an analysis in the monthly notices of the Royal Astronomical Society in early 2025, arguing that the evidence for evolving dark energy depends strongly on which supernova catalog is used. When using the Pantheon Plus supernova sample, the preference for evolving dark energy is weak. When using the Dark Energy Survey's 5-year supernova sample, it is strong. The two supernova catalogs cover different regions of redshift space and use different calibration methods. Their disagreement introduces an uncertainty that sits underneath the DESI result like an unresolved foundation problem. Efstathiou's critique does not invalidate the DESI findings, it contextualizes them. The evidence for evolving dark energy is real, but dependent on assumptions about supernova systematics that have not yet been fully resolved. Future data releases from DESI, combined with independent constraints from the Euclid satellite and the Vera Rubin Observatory, will be needed to determine whether the signal strengthens or fades. But here is what matters for the broader story. Even in the most conservative interpretation, the DESI results demonstrate that Lambda-CDM is no longer the only game in town. For the first time, a major observational program with world-leading precision has found that a model with evolving dark energy fits the combined cosmological data better than the standard model. The preference may not yet be definitive, but it is consistent, it has strengthened with additional data, and it points in the same direction as the Hubble tension towards something incomplete in the Lambda-CDM description of cosmic expansion. Step back now and look at the full picture that has developed over the course of this story. The Hubble tension reveals a disagreement between the expansion rate measured locally and the rate predicted by Lambda-CDM from the early universe. Webb has confirmed that the local measurements are not contaminated by the most commonly proposed systematic errors, though the debate between Rees and Friedman remains unresolved. The tension may be as large as 5 sigma or as small as 2, depending on which local measurement you trust. But it has not disappeared, and every independent method that avoids the distance ladder, including gravitational lensing time delays, continues to favor a value above Planck's prediction. The early galaxy problem reveals that structures formed in the first billion years of cosmic history with a speed and efficiency that Lambda-CDM's galaxy formation models did not predict. The most extreme claims of impossible galaxies have been tempered by the discovery that active galactic nuclei inflated some mass estimates, but a residual excess of roughly a factor of 2 persists. The astrophysical models within Lambda-CDM need revision, and the boundary between astrophysical revision and cosmological revision is not as clear as anyone would like it to be. The DESI results reveal that the combined weight of baryon acoustic oscillation data, cosmic microwave background measurements, and supernova observations may favor evolving dark energy over a cosmological constant. The statistical significance ranges from roughly 3 to 4 sigma, depending on the dataset combination, and the result is subject to ongoing debate about supernova systematics. But the direction of the signal has been consistent across 2 data releases and multiple analysis methods. 3 independent lines of evidence, 3 different instruments, 3 different methods. And all 3 point in the same direction toward a Lambda-CDM model that is not wrong, but may be incomplete. No single one of these results is sufficient to overturn a framework that has survived 25 years of precision testing. Scientists are rightly cautious about claiming that the standard model is broken on the basis of tensions that have not yet reached definitive statistical thresholds. The history of cosmology is full of anomalies that evaporated with better data, and the current tensions may yet be resolved by mundane explanations, unrecognized calibration errors, astrophysical processes that the simulations failed to capture, or statistical fluctuations that look more significant than they truly are. But there is a pattern forming, and the pattern is harder to dismiss than any individual result. When the Hubble tension stood alone, it was possible to treat it as a measurement problem. When the early galaxy excess appeared, it was possible to treat it as an astrophysics problem. When the DESI results emerged, it was possible to treat them as a statistics problem. But when all 3 pressures converge on the same model from independent directions, the question changes. It is no longer whether any single observation is strong enough to challenge Lambda-CDM. It is whether the cumulative weight of multiple independent observations, each individually below the threshold of certainty, collectively constitutes something that the model must answer. The phrase that has begun to circulate in cosmology meetings and journal discussions is concordant tension, a deliberate echo of the concordance model label that Lambda-CDM earned during its years of triumph. Where concordance meant that multiple independent measurements all agreed with the model, concordant tension means that multiple independent measurements are all disagreeing with it, gently, consistently, and from different directions. That is not a collapse. It is not a crisis in the sense of a building falling down. It is a crack thin, clean, and running through the foundation. The building still stands, the rooms still function, but the structural engineers have noticed, and they are not sleeping well. The question that remains is the one that matters most. Is this crack superficial, a cosmetic flaw that will be patched with better data and minor adjustments to the existing framework? Or is it structural, the first visible sign of a deeper incompleteness that will eventually force a fundamental revision of how we understand the universe? The answer to that question depends on what comes next. On the instruments being built, the observations being planned, and the theoretical frameworks being developed to make sense of what Webb and DESI and Planck have revealed. It depends on whether the tensions strengthen or dissolve as the data improve. And it depends on a question that goes beyond any single measurement or any single model, a question about what it means when the most successful framework in the history of a science begins, for the first time, to show the limits of its own success. That question is where we end. There is a story that physicists sometimes tell about the end of the 19th century. It is not entirely accurate as history, but it captures something true about the psychology of science. By the late 1800s, classical physics appeared nearly complete. Newton's mechanics described the motion of everything from cannonballs to planets. Maxwell's equations unified electricity, magnetism, and light into a single, elegant framework. Thermodynamics explained heat, energy, and the behavior of gases. The major structures of physical law seemed to be in place. A few small problems remained minor discrepancies, unexplained details at the edges of the picture, but the prevailing mood, at least among some, was that the fundamental work was essentially done. Lord Kelvin, one of the most prominent physicists of his era, is often quoted as saying that there was nothing new to be discovered in physics and that all that remained was more and more precise measurement. Whether he actually said those exact words is debated, but the sentiment was real. Classical physics had been so successful for so long that many practitioners believed the framework was essentially final. The remaining puzzles were treated as minor loose ends, curiosities that would eventually be absorbed into the existing structure without disturbing its foundations. Two of those loose ends were the ultraviolet catastrophe, a failure of classical theory to correctly predict the properly spectrum of radiation emitted by a hot object, and the null result of the Michelson-Morley experiment, which failed to detect the luminiferous ether through which light was supposedly traveling. Both problems were acknowledged. Neither was considered likely to require fundamental changes to the framework. They required exactly that. The ultraviolet catastrophe led to quantum mechanics. The Michelson-Morley null result led to special relativity. Within 3 decades, the two greatest revolutions in the history of physics had grown from problems that most experts considered minor. The foundation that appeared solid turned out to be an approximation extraordinarily useful, breathtakingly accurate within its domain, but incomplete at the boundaries where new phenomena emerged. That story is relevant not because the Hubble tension is guaranteed to produce another revolution. It may not. It is relevant because it illustrates something about how scientific frameworks actually fail. They do not collapse suddenly under the weight of a single devastating observation. They develop small inconsistencies. The inconsistencies persist. They resist easy explanations. And eventually, someone realizes that the inconsistencies are not bugs in the framework. They are the first faint signals of something the framework was never designed to describe. Lambda-CDM is in the early stages of that process. Whether the process will end in a minor adjustment or a major revision is genuinely unknown. But the pattern, the persistent discrepancies, the independent lines of tension, the failure of simple fixes to resolve them is recognizable. It is the pattern that precedes every significant shift in the history of physics. Not always. Sometimes the tensions dissolve, sometimes the measurements were wrong. But the pattern itself is worth paying attention to, because when it is real, the consequences reshape everything that follows. Let us be precise about what the crack is and what it is not. The crack is not a claim that Lambda-CDM is wrong. The model correctly predicts the statistical properties of the cosmic microwave background to extraordinary precision. It accurately describes the large-scale distribution of galaxies across the observable universe. It accounts for the relative abundances of light elements produced in the first few minutes after the Big Bang. It explains the observed acceleration of cosmic expansion. It provides a coherent framework for understanding structure formation across more than 13 billion years of cosmic history. These achievements are not diminished by the tensions Webb and DESI have revealed. They remain among the most impressive accomplishments in the history of quantitative science. The crack is also not a claim that everything scientists know is wrong. That framing, popular in certain corners of the internet and in sensationalized media coverage, misrepresents both the nature of the tensions and the nature of science itself. The vast majority of what Lambda-CDM describes remains observationally confirmed and theoretically sound. The tensions exist at specific boundaries, in specific measurements, under specific conditions. They do not invalidate the framework wholesale. They indicate that the framework may have a limited domain of complete accuracy, and that Webb is beginning to probe the edges of that domain. What the crack represents is something more subtle and, in some ways, more significant than either of those extremes. It is the possibility that the most successful model in the history of cosmology is not the final model. That it is an approximation, an extraordinarily good approximation, valid across an enormous range of observations, but an approximation nonetheless. And that somewhere in the gap between the model's predictions and the universe's behavior lies a piece of physics that we have not yet discovered. The distinction between a model being useful and a model being complete is one that scientists understand intuitively but rarely need to confront so directly. Newtonian gravity is useful. It describes the motion of planets, the trajectories of spacecraft, and the behavior of objects on Earth with more than sufficient accuracy for nearly every practical purpose. But it is not complete. It fails at very high speeds, very strong gravitational fields, and very large scales. General relativity provides the deeper framework that encompasses Newtonian gravity as a limiting case. Lambda-CDM may be in an analogous position, not wrong, but contained within something larger. Not broken, but bounded. The tensions Webb has revealed may be the first observational evidence of where those bounds lie. Now consider the specific proposals that theorists have developed to address the tensions, and what their current status tells us about how far we are from resolving the picture. Early dark energy is perhaps the most discussed proposal. The idea requires careful explanation because it is the single most developed attempt to resolve the Hubble tension, and understanding why it has not yet succeeded reveals something important about the nature of the problem. Recall that the cosmic microwave background carries an imprint of sound waves that traveled through the early universe. Pressure waves propagating through the hot plasma until atoms formed and the waves froze in place. The distance those waves traveled before freezing is called the sound horizon. That distance is the cosmic ruler embedded in the distribution of matter. When Planck measures the cosmic microwave background, it sees the angular size of that ruler projected on the sky. To convert that angular size into a physical distance, and from that distance into a prediction for the Hubble constant, Planck must know the actual length of the ruler. Here is where early dark energy enters. If an additional form of dark energy existed briefly during the first few 100,000 years after the Big Bang, present for a short window and then vanishing, it would have increased the expansion rate during that specific epoch. A faster expansion during the era when the sound waves were traveling would mean the universe was stretching more rapidly beneath the waves as they propagated. The waves would have traveled through more rapidly expanding space, and the resulting sound horizon, the distance they covered before freezing, would be slightly smaller than Lambda-CDM calculates. A smaller ruler changes everything downstream. When Planck observes the angular size of the hot and cold spots in the cosmic microwave background and converts that angle into a physical distance using a shorter ruler, the geometry of the calculation shifts. A shorter ruler at the same angular size means the spots are closer than the standard model assumed. And if the universe is slightly smaller at the epoch of the cosmic microwave background than Lambda-CDM predicted, the model must compensate by predicting a faster expansion rate to arrive at the same universe we observe today. The inferred Hubble constant goes up. If the increase is large enough, it closes the gap with the local measurement. The concept is elegant. The execution has proven far more difficult. Early dark energy models can be tuned to reduce the Hubble tension, but they tend to create problems elsewhere. The cosmic microwave background is not a single measurement. It is a power spectrum, a detailed curve showing how much temperature variation exists at every angular scale on the sky. Lambda-CDM fits that entire curve with remarkable precision. When early dark energy is added to the model, it shifts the curve. The Hubble constant moves closer to the local value, but the detailed shape of the power spectrum changes in ways that worsen the fit at specific angular scales. Features that Planck measured with extraordinary precision, the relative heights and positions of the acoustic peaks in the power spectrum, shift by amounts that the data do not support. There is a concrete example that illustrates the problem. In 2023, a detailed analysis by several independent groups found that early dark energy models that successfully raised the Hubble constant to 73 also predicted a higher amplitude of matter clustering in the late universe, a parameter called SATE. But observations of how galaxies are distributed and how their light is bent by intervening mass consistently measure a lower value of SATE than even standard Lambda-CDM predicts. This is itself a separate, milder tension in cosmology, sometimes called the SATE tension. Early dark energy, rather than relieving it, makes it worse. The fix for the Hubble tension aggravates the clustering problem, and the fix for the clustering problem would pull the Hubble constant back down. The tensions are entangled. Solving one tightens the other. Researchers describe it as a whack-a-mole problem. Push one discrepancy down and another pops up elsewhere. Several analyses have found that when all available data are considered simultaneously, the cosmic microwave background, baryon acoustic oscillations, supernova distances, galaxy clustering, and weak gravitational lensing, early dark energy models do not provide a clearly better overall fit than standard Lambda-CDM. They trade one tension for another. The net improvement is marginal at best. Modified gravity proposals face similar challenges. Altering the behavior of gravity at cosmological scales can change the expansion history in ways that affect the Hubble constant. But the modifications must be carefully constrained to avoid conflicting with the exquisitely precise tests of general relativity that have been conducted in the solar system and through gravitational wave observations. The parameter space that simultaneously resolves the Hubble tension and satisfies all other constraints is narrow, and no single modified gravity model has emerged as a compelling consensus solution. Evolving dark energy, the direction suggested by the DESI results, offers a different approach. If dark energy is not a cosmological constant but a dynamic field whose equation of state changes with time, the expansion history of the universe differs from Lambda-CDM's predictions in ways that could potentially address both the Hubble tension and the DESI anomaly. But the theoretical landscape for evolving dark energy is vast. Quintessence models, phantom dark energy models, and more exotic scenarios each predict different evolution patterns, and the data are not yet precise enough to distinguish between them or to confirm that any of them is correct. The most honest summary of the theoretical situation is this: many ideas exist, none has succeeded. The Hubble tension has been known for nearly a decade. Hundreds of papers have proposed modifications to the standard model that might resolve it. Not one of those proposals has achieved a clean, simultaneous fit to all available data without introducing new tensions or fine-tuning problems. This is not because theorists lack creativity. It is because the constraints are extraordinarily tight. Lambda-CDM fits such a wide range of observations so well that any modification must thread a needle, improving the fit in one place without degrading it everywhere else. So far, no modification has managed it. That difficulty is itself informative. It suggests that, whatever the correct explanation turns out to be, it is not a trivial adjustment. It is not a minor patch applied to one corner of the model while leaving everything else untouched. The interconnectedness of cosmological parameters, the way a change in one propagates through to many others, means that resolving the tensions may require a coordinated shift in multiple aspects of the framework, simultaneously. And coordinated shifts of that kind, in the history of physics, tend to accompany genuine conceptual advances rather than incremental corrections. The instruments that will determine whether the crack deepens or closes are already being built. The Nancy Grace Roman Space Telescope, scheduled for launch by NASA, will survey the sky with a field of view 100 times larger than Webb's, though with lower resolution. Its primary cosmological mission is to measure the expansion history and the growth of cosmic structure through weak gravitational lensing and supernova observations. Roman will provide an independent measurement of whether dark energy is constant or evolving, with precision sufficient to either confirm or challenge the DESI signal. If Roman's data agree with DESI, the evidence for evolving dark energy will be difficult to dismiss. If they disagree, the situation becomes more complex, but potentially more informative. The European Space Agency's Euclid mission, launched in 2023, is already collecting data. Its goal is to map the geometry of the dark universe by observing the shapes and distributions of billions of galaxies across more than a third of the sky. Euclid's weak lensing measurements will constrain the clustering of matter in the late universe, providing an independent check on Lambda-CDM's predictions for structure growth. Early results are expected to contribute meaningfully to the tension landscape by 2026 and beyond. DESI itself is continuing to collect data. Its third data release, incorporating additional years of observations, will either strengthen the evolving dark energy signal or reveal it as a fluctuation that diminishes with more statistics. The experiment's designers built it specifically to answer this question, and its dataset is growing rapidly. On the Hubble tension front, Webb will continue to observe Cepheids, tip of the red giant branch stars, and other distance indicators in additional galaxies. The disagreement between Rees and Friedman, between the SH0ES measurement of 73 and the Chicago-Carnegie measurement of 70.4, will eventually be resolved by the sheer volume of data. Either the two methods will converge on the same value, confirming or denying the tension with Planck, or they will continue to disagree, pointing to an unrecognized systematic difference between the methods themselves. Either outcome will be informative, neither will be uninteresting. The gravitational lensing approach, pioneered by the TD-COSMO collaboration, will also expand. More lensed quasar systems will be identified and analyzed, providing additional independent constraints on the Hubble constant that bypass the distance ladder entirely. If lensing continues to favor a high value, the case for a genuine cosmological discrepancy strengthens regardless of which distance ladder method is correct. Within the next 5 to 10 years, the cosmological community will have access to a dataset of unprecedented scale and precision. The question is whether that dataset will close the crack or widen it. Both outcomes would represent significant scientific progress. A closed crack would mean that Lambda-CDM truly is the correct description of the universe at all accessible scales, and that the current tensions were artifacts of incomplete data or unrecognized systematics. A widened crack would mean that the universe contains physics beyond the standard model, new fields, new forces, new phenomena that our current framework does not capture. There is a philosophical dimension to this that deserves acknowledgement, and it is the dimension that separates the current moment from a routine measurement dispute. In the history of science, the most productive crises have not been the ones where a model was spectacularly wrong. They have been the ones where a model was almost right. Newtonian gravity was almost right. It described the motion of planets with extraordinary accuracy for 2 centuries. The tiny anomaly in Mercury's orbit, a discrepancy of 43 arcseconds per century in the precession of its perihelion, was known for decades before Einstein's general relativity explained it. That anomaly was not a failure of Newtonian physics in any dramatic sense. It was a whisper from a deeper framework, audible only because the measurements had become precise enough to hear it. The Hubble tension has that quality. It is not a thunderclap announcing that cosmology has collapsed. It is a whisper, a 5 to 6 km per second per megaparsec discrepancy in a number that is roughly 70, a difference of less than 9%. In almost any other field, that would be considered excellent agreement. In precision cosmology, it is a signal, because the error bars have shrunk to the point where 9% is many standard deviations away from acceptable. The early galaxy excess has a similar character. The universe did not produce galaxies that flagrantly violate the laws of physics. It produced galaxies that are roughly twice as abundant as the models expected at a particular epoch, not 10 times, not 100 times, twice. In a less precise field, a factor of 2 would be unremarkable. In a field that aims to match observations to predictions within tens of percent, it is a problem. And the DESI signal is perhaps the subtlest of all. Dark energy may not be constant. Its equation of state may differ from -1 by a small amount that varies slowly with cosmic time. The deviation is not dramatic. It is a gentle curve where the model predicts a flat line. But the curve has been detected by 2 independent data releases using 2 independent analysis pipelines, and it persists across multiple combinations with external data. Each of these tensions is quiet. Each is modest. And each, independently, could be explained away. That is what makes the convergence so striking. 3 quiet signals from 3 independent directions, all pointing toward the same conclusion, that the standard model is not capturing everything that the universe is doing. The probability that all 3 are simultaneous statistical flukes, unrelated to each other and unrelated to any real physical phenomenon, is small, not 0. But small enough to warrant serious attention. There is a concept in structural engineering called a hairline fracture. It is a crack so thin that it is invisible to the naked eye. It does not compromise the immediate function of the structure. A wall with a hairline fracture holds weight. A beam with a hairline fracture supports its load. But engineers take hairline fractures seriously because they propagate. Under continued stress, they grow. And by the time a hairline fracture becomes visible to an untrained eye, the structural damage is often far more extensive than it appears. Lambda-CDM may have a hairline fracture. Webb may be the instrument that made it visible. And the stress that will determine whether it propagates or stabilizes is being applied right now by every new observation, every new data release, every new attempt to fit the combined weight of modern cosmological data into a framework built 25 years ago. The deepest implication of everything described in this story is not that cosmology has failed. It is the opposite. Cosmology has succeeded so completely, with such extraordinary precision, that it has reached the resolution necessary to detect its own limitations. The Hubble tension is not evidence that scientists were careless. It is evidence that they were meticulous, so meticulous that a discrepancy of a few kilometers per second per megaparsec can no longer be hidden in the noise. The early galaxy excess is not evidence that models were foolish. It is evidence that observations have advanced to the point where the approximations buried in the models are finally being tested against data that can distinguish between an approximation and reality. This is what scientific progress looks like at the frontier. Not a dramatic overthrow, not a moment where everything changes, but a slow tightening of precision, a gradual narrowing of uncertainty until the gap between prediction and observation becomes impossible to ignore. The framework does not shatter. It develops a tension, a real, physical, measurable tension between what it says should happen and what the instruments say is happening. And then the work begins, the real work. The work of figuring out what the framework is missing. Whether it is a new particle, a new field, a new property of dark energy, a modification of gravity, or something so unexpected that no one has yet imagined it. That work is underway now, in hundreds of offices and observatories and computing centers around the world. It is being done by people who built their careers on Lambda-CDM and who understand its power intimately. They are not dismantling the model they devoted their lives to. They are doing something harder. They are acknowledging that the model they love may not be the final word, and they are looking honestly and rigorously for whatever comes next. Adam Rees, whose measurement of the Hubble tension is one of the defining results of 21st century cosmology, framed the situation with characteristic directness. We need to find out if we are missing something on how to connect the beginning of the universe and the present day. That sentence carries more weight than it appears to. Missing something is not the language of failure. It is the language of exploration. The beginning of the universe and the present day are separated by nearly 14 billion years of cosmic evolution, expansion, cooling, structure formation, the emergence of dark energy as the dominant component. Lambda-CDM describes that evolution with 6 parameters and a set of well-tested physical laws. If the description is incomplete, the incompleteness lives somewhere in that vast stretch of time. Finding it means identifying a process, a transition, a phenomenon that the model does not currently include. The universe is not waiting for us to figure this out. It is expanding, accelerating, forming structures, and evolving according to whatever laws actually govern it, whether or not those laws match the ones we have written down. Webb is watching. DESI is mapping. Euclid is surveying. Roman is being prepared. The data are accumulating. And the crack thin, quiet, persistent is either growing or stabilizing with every new observation. One way or another, the next decade will bring clarity. If the tensions dissolve, Lambda-CDM will emerge stronger than ever, a model so robust that it survived the most precise scrutiny ever applied to a physical theory about the cosmos. That would be a remarkable outcome, a vindication of 25 years of theoretical and observational work, and a demonstration that the universe is, at the largest scales, simpler than some of us feared. If the tensions deepen, something extraordinary awaits, a new piece of physics, hidden for decades inside a framework that was too successful to question and too precise to ignore. The first real modification to our understanding of cosmic evolution since the discovery of dark energy in 1998. Not a collapse of the old model, but an expansion of it, the way general relativity expanded Newtonian gravity, preserving everything that worked while revealing a deeper structure beneath. Either outcome is a victory for science. Either outcome justifies the billions of dollars, the decades of engineering, the thousands of careers devoted to building the instruments that made these measurements possible. But there is something in the second outcome, the one where the crack is real, that carries a weight beyond the scientific. It would mean that the universe is not yet fully described by any framework that human beings have constructed. That after a century of extraordinary progress, after mapping the cosmic microwave background and cataloging billions of galaxies and measuring the expansion of space to within 1%, there is still something out there that we do not understand. Something woven into the fabric of cosmic expansion, or hidden in the first moments after the Big Bang, or embedded in the nature of dark energy itself, that our best model does not capture. That is not a failure. It is an invitation. The universe is telling us, through the language of precise measurement and irreducible discrepancy, that there is more to learn, that the story is not finished, that the model, magnificent, precise, triumphant, is a chapter, not the book. 1,000 confirmations cannot teach you anything new. They tell you that you are right, and they tell you it beautifully, and they give you confidence that the path you are on leads somewhere solid. But they cannot show you what you are missing. One crack can, one measurement that does not fit, one number that refuses to agree. One observation at the edge of the visible universe that whispers, quietly but unmistakably, that there is something here your model did not expect. James Webb may have found that crack. It may be the first place where the most successful framework in the history of cosmology meets its own boundary. Not a wall, not an ending. A boundary, the kind that, when crossed, reveals not that you were wrong, but that there was always more universe than your equations had room for. The golden mirror is still collecting light. The data are still arriving. And somewhere in the gap between what the model predicts and what the telescope sees, the next chapter of cosmology is waiting to be written. We do not yet know what it will say. But for the first time in 25 years, we know it will say something new.